Okay, good evening everybody. As I told you that I'm going to solve with you several examples or three more examples on tension members. We are going to solve them together now. This will be a good exercise for you if you want to practice for the quizzes or for the homework assignments. Now we have in this problem a given truss as such where we are having three marked members similar to your homework assignment exactly. Now we are having member 1. This is a bottom chord member. We obtained the internal forces in this member due to the dead load and due to the life load case 1 and 2 and due to the wind loads left and right. Now it is required to determine the positive design force and the negative design force for member 1, 2 and 3. Member 2 is a diagonal member and member 3 is a vertical member. Now let us start for design of member 1. Let's assume that it's given to us in the problem that this member is bolted and the bolt diameter is 16 millimeters. Okay? Let me first determine the positive design force. For the positive design force, I will take the dead load. It's obligatory. It's no choice. We are going to take this 10 ton. For the life load, we either take case 1 or case 2 or both of them combined, because we have the right to add the two components of or the two cases of the life load, or take one of them according to the design force we are adding. Since we are searching for the maximum positive, then I'm going to take life load case 1, which is 9 tons. For the wind, we shall either take case of wind left or wind right. We cannot add them together, even if they are both increasing the design force that we are searching for. But here, since we are searching for the positive, we are going to take the least negative, which is negative 1. Then we are going to plug in the first load combination equation, which is 1.4 dead. This will be 14 tons. The second load combination equation, which is 1.2 dead plus 1.6 life. We are substituting here the dead load by 10 and the life load by 9. We are going to get 26.4. For the ultimate load, or the load combination number 3, we are taking 1.2 dead plus 0.5 life plus 1.3 wind. If you did that, we are going to get 15.2 tons. For the ultimate load number 4, the load combination number 4, we are taking 0.9 dead plus 1.3 wind. So I'm going to take the 10 tons and the negative 1. We get here positive 7.7. Now we are going to take the maximum value, which is obtained from the second load combination equation. We are going to write here 26.4. Okay? For the negative design force, we have to take the dead load by 10. The life load is negative 2. And the wind load, we can either take wind left or wind right, but we are going to take wind right since we are searching for the maximum negative design force. Now, if you plugged in the first load combination equation, this is not applicable because you are going to get a positive design force. 1.4 times 10 is 14. And the second one, also you are taking 1.2 of the dead minus 2 multiplied by 1.6, so you are going to get a positive design force. So this means that this is also not applicable since we are searching for the maximum negative. And for the third load combination equation, we are taking 1.2 of the dead and negative 2, which is the life load, by its factor 0.5, and negative 2 by the wind factor, which is 1.3. Also, it will give us a positive value, so it is also not applicable because we are searching for the negative. And for P ultimate 4, we are taking 0.9 of the dead, negative 2, which is the wind, multiplied by 1.3, its factor. Also, we are getting, in this case, a positive design force, so it is not applicable. So this means that none of the load combinations will give us a negative design force, so this member is a pure tension member. This is not applicable, so this is a pure tension member. And the design force that we are going to use here is 26.4. Now let us start designing this problem. So we are given here that the design force P ultimate is 26.4 and the connections are bolted with a bolt diameter of 16 millimeters. And of course the member is found in the bottom chord. This is the bottom chord. Of course the members that are found in the top chord and the bottom chord should be composed of two angles back to back, regardless to the design force and the length. The length of this member, it says here that the horizontal projection is 3 meters, but basically the member is inclined and the angle of inclination is 1 to 10. It means that we are having the member is like this. This distance here is 3 meters and the slope is 1 to 10. What does this mean? It means that the ratio of this side to this side is 10 to 1. يبقى this should be 0.3 and this is 3 meters. So if you want to get this length, you can get root 3 square plus 0.3 square, or you can say that this length, this angle is theta, and we can say here theta is tan inverse 1 over 10, which is 5.71 degree. Okay? Therefore, we can say that the length of this member is 3 over cosine theta, which is 3.05. 3.02. If you want to be accurate, then we are getting the exact length. Now the first step is the type of cross-section. The type of cross-section, it has to be two angles back to back. Why? Because this is a chord member. The second condition is the stiffness condition. We say here that L over I minimum should be less or equal to 300. Since we choose two angles back to back, you are having I minimum is 0.3a, because when we are having two angles back to back like this, the axis that is giving the minimum radius of gyration is the x-axis. If the side of the angle is A, and of course the length or the other side is also A, because this is equal leg angle, then we are having I minimum is equal to Ix is equal to 0.3a. Then we are having the length over I minimum should be less or equal to 300. يبقى therefore 302 over 0.3a is less or equal to 300. Therefore we get the first condition that a should be bigger than 302 over 0.3 times 300, and this should not be less than 3.35 centimeter. This will be the first condition we are going to use for the selection of this angle. Okay? Right. Let me go to the other. This is the first step that we followed. The second step that we determined the stiffness condition. The third step I will go to number 3, the construction condition. We know that the angle will be bolted to the gusset plate. There will be bolts here like this. This is the angle leg A, and this is the thickness T. This distance here, which is A minus T, must be sufficient to accommodate the bolt. The bolt diameter is dB. Then it says that A minus T should be bigger or equal to 3 times the bolt diameter. We did not yet select the angle, so we are going to leave the condition as it is and put in mind that A minus T should be bigger or equal to, he told me that the bolt diameter is 16 millimeter, so this is 3 multiplied by 1.6, so it should be bigger or equal to 4.8 centimeter, and this is the second condition. The first condition, that the angle leg itself, the angle leg should not be less than 3.35 centimeter, and the difference between the angle leg and its thickness should be not less than 4.8, so that we can accommodate the bolt. If we take a section here, this is the angle, and here we are having the gusset plate, and this is the bolt. This is the bolt diameter, and we need that this distance, which is A minus T, of course this is A, and this is T. It must be sufficient to accommodate the bolt. It will have to be at least 3 times the bolt shaft diameter, which is dB. So this is the second condition. The third condition will be the area. Now, or the fourth condition will be the area required. Take care. When we studied tension members, we said that the tension member can fail in the middle, and this we called the gross section yielding failure mode, and it can fail at the bolt, and this we called the net section fracture. Okay? So for the gross section yielding, we said that phi P nominal should be bigger or equal to P ultimate. P ultimate is the design force that we calculated together, which is 26.4. And phi is 0.85 in case of the gross section yielding, and P nominal is the cross-sectional area of the member. The cross-sectional area is composed of 2 angles. Then it is N multiplied by area gross multiplied by the yield stress, because this limit state is yielding. So we assume that the section reached the yield stress. So this is F yield is bigger or equal to P ultimate. From there, area gross will be equal to P ultimate over 0.85 times N times F yield. Now we need to substitute. Here we are getting the area of one angle only, of one angle. The section is composed of two angles as we know. يبقى from there, the area of one angle will be the design force, which is 26.4 over 0.85 times 2, because we are having two angles in the cross section, times F yield, because we are using steel 37. We are using steel 37 with F yield 2.4 ton per centimeter square and F ultimate 3.6 ton per centimeter square. So if you did that, you are going to get the first condition for the area, and it will be 6.47 centimeter square, and this is condition number 3. This is not only the failure mode. Now, if you selected the area of the angle to be not less than 6.47, you will guarantee that the angle will not cut in the middle. How about in the section or at the connection? I mean, in this case, we need to apply the net section fracture limit state. For the net section fracture, also we are having the strength condition phi P nominal is bigger than P ultimate. But phi, which is the strength reduction factor, is different this time. It is 0.7, because we are talking about a different failure mode. Here, we allowed the steel to reach the yield stress. Still, we are having reserve strength. So we reduced, we have here the strength reduction factor is 0.85. But at the connection, we allowed the section to reach the ultimate strength. There is no reserve strength anymore. We are using the maximum stress that can be supported by the member. And that's why here we reduced the factor of safety. Instead of 0.85, we used 0.7. Now P nominal, we are having two angles, then this is N, the number of angles in the cross section, and this is the area gross of the angle. We have to multiply this by the shear lag factor U and the net area factor beta. The factor of U, or the value of U, is 0.75 if the members are bolted, and 0.85 if they are welded. And beta is 0.85 if the members are bolted, and 1 if they are welded. So this to take care of the shear lag factor, and this factor is to account for the net section or the gross section of the angle to support the force. Of course, we have to multiply by F ultimate, which is the accepted stresses in this limit states. So this here, these factors, they determine the effective area of the angle. Now, N is the number of angles in the cross section, and area gross is the gross area of the angle. U is a factor that accounts for the shear lag, and we said that it is either 0.75 in case of bolted and 0.85 in case of welded. And 0.80 and beta is to account whether you are taking the gross area or the net area. You are taking the gross area if the member is welded, so beta will be 1. And you are going to reduce the area a little bit to account for the bolt hole, and will be taken 0.85 in case of bolted connections. F ultimate is 3.6, as we said, for steel 37, and this should be bigger or equal to P ultimate. Therefore, if I want to get an estimation for the gross area of one angle, then this will be P ultimate over phi times N times U times beta times F ultimate. Let us substitute here. The value of P ultimate is 26.4 and phi is 0.7. N is 2 because we are having two angles in the cross section. U is the shear lag factor. Since the member is bolted, we are going to take 0.75 And beta, since the member is bolted, we have to take the net area, but we cannot calculate the net area now because I don't know the area and I don't know the thickness of the angle yet. So I'm going to assume that beta is 0.85. That is an approximation because we don't know exactly how much is the net area compared to the gross area. We are assuming it 0.85. As long as you did this approximation, you will have to check later on after you select the angle that this condition or this limit state is really satisfied. And of course, P ultimate or F ultimate is 3.6. From there we get the area and it will be 8.73 centimeter square, and this is condition number 4. So let us now list the condition based on which we are going to select the angle. The 4 conditions that we have reached so far. So the 5th step is the selection of cross section. From condition number 1, we said that A should be bigger or equal to 3.35 centimeter. From condition number 2, which is the construction condition, we said that A minus T should be bigger or equal to 4.8 centimeter. From condition number 3, we said that the area gross should be bigger and equal to 6.47 centimeter square. And from condition number 4, area gross should be bigger and equal to 8.73 centimeter square. Of course, this condition will supersede because it is requiring more area. So the net section fracture condition will be followed. Now I want to select an angle from the table such that A is bigger than 3.35. You will find that the first angle in the table, 45 by 45 by 5, is satisfying this condition because A is 4.5 centimeter. And A minus T should not be less than 4.8. You will find that the first angle in the table is 55 by 6 because 55 minus 6 gives 49 millimeter, which is 4.9 centimeter bigger than the construction condition. And if we search for the angle that satisfies the area, you will find the first angle that satisfies the area will be angle 60 by 60 by 6. Therefore, use 2 angles, 60 by 60 by 8, and the area of which we get this from the table. It is 9.03 centimeter square. Before we go into checking for the net section fracture, let me show you here. What is the value of A? Therefore, I'm having A is 6 centimeter. This is bigger than 3.35 centimeter. Then okay. And A minus T is equal to 6 minus 0.8, 6 centimeter, which is the angle leg, and the thickness is 8. Remember, the angle is like this. This is 60, and this is 8, and this is 60. So this means that A minus T is equal to 6 minus 0.8, which is 5.2. This is bigger than 4.8 centimeter. Then this condition is satisfied and this condition is satisfied. And of course the area is 9.03 and this is bigger than 8.73. Therefore my selection is okay. Now we did one assumption that we assumed that the net area is 85% of the gross area. Why did we do this? Because we did not have the dimensions of the angle and we did not have the area of the angle. Now we can check for the net section fracture. Take care. In this step, you are graded that you selected the correct angle. You have to satisfy the three limits. The limit of A based on the stiffness condition, and A minus T based on the construction condition, and the area gross, whichever is bigger from here, which is 8.73. Your selection will have to cover the three limits. Okay? Now, the last step in this member is to check on the net section fracture. Number 6, check on net section fracture. How does the angle look like? The angle looks like this. Now we are going to have, this is the bolt hole, and we increase the bolt hole by 2 millimeter so that we can easily install the bolt. And this will be the net area. يبقى the net area will be the gross area minus the area deducted due to the presence of the hole, which will be D plus 0.2, and the thickness here is 0.8 centimeter. How did I know this? Because this angle is 60 by 8. 60 is the angle leg, is the length of this leg here, 6 centimeter, and this is 6 centimeter, and the 8 is the thickness, 0.8 centimeter and 0.8 centimeter. Okay? So if you want to get the hatched area, you will have to deduct this rectangle, which is, the diameter of the bolt is 1.6 centimeter, so this is 1.8 multiplied by 0.8. Again, what is the 1.8? It is the hole diameter, which is the bolt diameter plus 0.2, and 0.8 is the thickness of the angle. If you did this, you are going to substitute here by the area of the angle, and you are going to get 7.59 centimeter square. Therefore, phi P nominal will be 0.7, which is phi, multiplied by n, which is the number of angles. We are having 2, and multiplied by area net, and multiplied by u, and then multiplied by F ultimate. Where is beta? Already, beta is taken into consideration because we substituted here with the net area, not the gross area. Before, when we were selecting the angle, instead of writing area net, we wrote area gross multiplied by beta, because beta is accounting to the amount of deduction due to the presence of the bolt hole. So we don't use beta anymore here. So we are having here 0.7 times 2 times the net area, which is 7.59, times u, the shear lag factor is 0.75 as long as the connection is bolted, and the value of F ultimate is 3.6. If you did this, you will find that it is 28.7. Take care. How much is the applied design force? It is 26.4 according to the load combination that we did. And how much is the nominal reduced resistance? It is 28.7. So this is bigger than P ultimate. Therefore, it is safe. My final choice, select two angles 60 by 60 by 8 back to back. This is for the design of member number 1. Okay, let us go to member number 2. For member 2, he told me check the safety of that member. check the safety of two angles 50 by 5 star shape. And the connections are bolted with a bolt diameter of 12 millimeter. This is a different style of asking you the question. Now in member 2, I don't want you to design. I told you that this member is already composed of two angles 50 by 5 star shaped and the connections are bolted. Please verify that this section is satisfactory. We have to satisfy. We have to check satisfaction of the design force and the construction condition and the strength condition. So we will start with the design force. I will get the positive design force here. So for the positive design force, the dead load will be 3. The life load, I will take either the 3 or the negative 1.5. So I will take here the 3. For the wind load, I will take either the negative 0.5 or the 5. So for the wind, I will take the 5. يبقى P ultimate 1, which is 1.4, which is 1.4, the dead load will be 4.2 tons. P ultimate 2, which is 1.2 dead plus 1.6 life, this will be 8.4 tons. For the third load combination, I will take 1.2 dead plus 0.5 multiplied by the life load, which is 3, plus 1.3 multiplied by the wind. We get here a value of 11.6. And P ultimate 4, I will take 0.9 the dead load plus 1.3 the wind load, and this will give us plus 9.2. So this means that the maximum design force that we are going to work here will be 11.6. So here we are having 11.6. طيب, for the negative design force, I will take the dead load to be 3 and the life load. Either we take that one, case 1, or case 2, or both of them combined. But since we are searching for the negative, we have to take the life load to be negative 1.5. And for the wind, I will take the wind load to be negative 0.5, of course, because we are searching for the maximum negative. If we substituted in the 4 load combination equation, you will find that the first one will give you a positive design force, so it is not applicable. The second one, the same. When you take 1.2 dead plus 1.6 life, you are going to get a positive design force. So this is not the one that you are searching for. And P ultimate 3 also, you are taking 1.2 dead plus 0.5 life load plus 1.3 wind. Again, it will be a positive design force, so it is not applicable. And the last one, 0.9 dead and 1.3 wind, will also be not applicable. So this will be a pure tension member, and none of the load combination will give me a compression design force. يبقى I will have to check this member to resist a tension force of 11.6. طب, let us see. We are solving this problem with a different style. Most of you, when you get this question, you neglect what I gave you. You neglect that I gave you the answer. I told you that we are having two angles star shape 50 by 5. We don't go through the steps of the solution. Now, for the type of cross section, we are having two angles star shape. This is correct. Why? Because member 2 is found in the web member. The web members, these members can be either one angle or two angles star shape or two angles back to back according to the design force and the length. Now he used one of these acceptable options, then the type of cross section is valid. If he used in member 1, for example, two angle star shape, it would be wrong, and you should not proceed with the checking process. You have to tell him that the type of cross section is wrong, it does not fit with what we have to use. So this is okay. Okay, for the stiffness condition, we need to get the length. Take care. Let me elaborate on this part here of the truss. This horizontal distance is 3 meters, and this vertical distance is 5 meters. This angle is not a right angle triangle. يبقى how can you get the length of this member? Take care. We are having here the slope is 1 to 10. What does this mean? It means that if we had a horizontal line like this, then this distance will have to be how much? It will have to be 1/10 of the horizontal distance. The horizontal distance here is 3, يبقى therefore this value is 0.3. يبقى there remains for us from the 5, 4.7. يبقى if you look to this right angle triangle, you know 4.7 and 3, you can get the length of the hypotenuse by Pythagoras. يبقى therefore you can say here that the length is equal to root 4.7 square plus 3 square, and if you did this, then you are going to get the length 5.6 meters. For the stiffness condition, we are having L over I minimum should be less or equal to 300. The value of I minimum for the two angle star shape is 0.385 of A. يبقى therefore we are having 560 over 0.385 multiplied by A. This is 300. From there, the value of A should be bigger or equal to or instead of doing this, we know the value of A. We have to check whether L over I is really less than 300 or not. So substitute the value of L, which is 560, and substitute the value of I minimum, which is 0.385 of A. What is A? He told me that the angle leg is 5 centimeters, then this is 5. When you do this, it will be 290.9. So this is less than 300, it's okay. Suppose that this condition is not satisfied. When you calculated L over I, it was bigger than 300. Then you have to stop and tell me your angle is not satisfactory. You don't have to proceed with the rest of the steps. But we are checking step by step. We verified here that the cross section is acceptable, and also the stiffness condition, it is acceptable because L over I is less than 300. Now you have to check the construction condition. Number 3, the construction condition. The section looks like that. and we are having the gusset plate here, and there is a bolt here, and we are having a bolt there. The angle leg is 50 millimeter, and the thickness is 5 millimeter, and the bolt diameter is 12 millimeter. So we say here A minus T will be 5 minus 0.5, it is 4.5 centimeter. And 3 times the bolt diameter will be 3 times 1.2. Take care, we are putting here the bolt diameter, not the bolt hole. As he gave me the bolt diameter is 12, so this is 3.6. This means that A minus T is bigger than 3 times the bolt diameter. Then the third condition is okay. The fourth condition is the strength condition. Remember, here we are not getting the area of the angle. We know that the area of the angle is 4.8 centimeter square. From where did I get this area? I got this from the table corresponding to 2 angles back to back 50 by 5. So I'm going to straightforward plug in the equation of the gross section yielding. We are having phi Pn. I want to see how much the angle can support. So the value of phi is 0.85, and we are having 2 angles in the cross section, so n is 2. And we are having the area gross of the angle is 4.8, and F yield for steel 37 is 2.4. So if you calculated this, you will find that the value is 19.6 ton. This is bigger than 11.6 ton, therefore it is okay. We checked for the gross section yielding and for the construction condition, and it's fine. There remains for us the net section fracture. For the net section fracture, remember that one angle looks like this. This is 5 millimeter, and this is 50. This is 50, and this is 5 definitely. And we are having here the bolt hole, the hole diameter now. We are having 1.2 plus 0.2, which is 1.4 centimeter. Okay, we need to calculate the net area. Here we are having everything. We don't need to. Let me write all of this in millimeter better so that you are not confused. This is 12 plus 2, 14 millimeter. Now, if I want to get the net area, this is 4.8 minus the rectangle deducted due to the presence of the bolt hole, which is 1.4 centimeter multiplied by 0.5. So this will be 4.1 centimeter square. Therefore, phi P nominal will be the value of phi is 0.7 times n, which will be 2, times area net. We are no longer putting area gross times beta because we are not selecting the angle. We know the angle and we calculated the net area accurately. So I don't need to assume beta 0.85 anymore. And the value of u, which will be 0.75 because this section is bolted, and F ultimate, which is 3.6. So we substitute here. Area net is 4.1 and u is 0.75 and F ultimate is 3.6. So we get this value, and it is 15.5 tons. This is bigger than 11.6. Therefore it's okay. We found that for this member it is satisfying the type of cross section, the angle leg according to the stiffness, A minus T according to the construction, and the strength condition based on the gross section yielding, it is sufficient, and for the net section fracture it is sufficient. Take care, the number that you are getting here must be bigger than the number that is caused by the applied forces. Okay? Type. The last question will be check on member 3. Member 3, I'm going to design member 3. So design a suitable section. Here the connections are welded. Okay? So for member 3 solution, I will have to determine the design force first. For the positive design force, I will have to take the dead load even if it is negative, because the dead load, no one can remove the dead load, so it is 2. The life load, since I'm searching for the maximum positive, I'm going to take the least negative, which is negative 0.25. And for the wind, either that we take the wind left or the wind right, we cannot combine them together because the wind cannot blow from both sides at the same time. So the wind will be 3 tons. Based on the first ultimate or the load combination, 1.4 of the dead is 2.8 tons. The second, which is 1.2 dead plus 1.6 life, if you did that, you will get a value of 2. And P ultimate 3, we are taking 1.2 dead plus 0.5 life plus 1.3 of the wind, and this will be 6.175. And P ultimate 4, I'm going to take 0.9 of the dead plus 1.3 of the wind, and this one will be 5.7 tons. Now, this value is the biggest value. So this will be the design force. Again, for the negative design force as before, the dead load will be 2. The life load, since I'm searching for the negative, I have the right to add them together. So this is negative 1.25. For the wind, I'm going to take the least positive, which is 2. Again, you will find that the design force in this case is not applicable. None of the load combination equations will give you a value, a negative value. Therefore, it will be a pure tension member. So here I will have 6.2, and this value is not applicable. Okay? So let us start the design process. So we are having here the design force is positive 6.2. The connections are welded as we stated here, and the length of the member, of course this line here according to the geometry given is parallel to this line, and we are having this distance is 5, so this is 5 meters. Okay, and the type of cross section, since the member is found in the web members, because it is a vertical, the design force is less than 8 tons and the length is more than 3 meters. then I'm going to use two angles star shape. Okay? For the construction, we don't have construction condition. There is no limitation on the difference between A and T because we are not installing anything there. So I don't have no construction condition because the member is welded. For the stiffness, we are having L over I minimum is less or equal to 300. The length is 500 over I minimum. For the star shape, this axis is giving us the minimum inertia, and it is 0.385 of A. So this is 0.385 of A is less or equal to 300. Therefore, A should be bigger or equal to 4.33 centimeter, and this is condition number 1. Okay, then for the design force, we need to get the area. The area required. For the gross section yielding, we say that the area of one angle will be equal to the design force over N times phi, which is 0.85 times F yield. So we are having here, this is 6.2 over N, which is the number of angles in the cross section. We are having 2 angles. The strength reduction factor is 0.85 and F yield is 2.4. From there we get the area is 1.5 centimeter square. For the net section fracture, the gross area of the angle will be P ultimate over N times 0.7 times area gross. Times U times beta times F ultimate. The value of N is 2, and the value of U, because this member is welded, the value of U is 0.85, and this member is welded, so there is no deduction due to the presence of the bolt hole, so beta is 1, and the value of F ultimate is 3.6. From there I will get the required area, and it will be 1.44 centimeter square. Of course, this area will govern. Finally, when I want to select the cross section, let me erase this here. For the selection of cross section, we are having the first condition A should be bigger or equal to 4.33 centimeter, and the second condition, I don't have construction condition, the area gross should be bigger or equal to 1.5 centimeter square. If you look to the first angle in the table, angle 45 by 45 by 5, you will find that it is satisfying the area and also is satisfying A. Therefore use 2 angles 45 by 5 as star shape. Okay, this is our final selection. Of course, we don't go back to check the net section fracture anymore because we did not do an approximation. We did not assume that beta is 0.85, so I don't need to go back and check for the validity of the net section fracture. Okay, I hope that this is clear, and we'll see you then in the compression members.